Okay, so I got here to film the video over section 12.9, and I kind of planned out my lecture before I came in this room. So this is the homework problem. One of the problems I assigned, I decided we should skip because the author, this problem is just like a problem in section 12.8, and the author interprets the problem differently in section 12.9 than it does in 12.8, and it wouldn't help you understand the material if I presented it in this section. So we'll just skip this, and maybe I'll talk about what the confusion is at some point, but maybe I won't. So anyways, the homework assignment is short, and the author could have made sections 12.9 and 12.10 into one long section. So if you perfect section 12.9, then section 12.10 will kind of fit nicely and it won't be so horrible. When I do the video, eventually I'm going to do a bunch of problems from the book and a few made up problems just so when you're doing your take-home test, you might have something else to watch just in case you get stuck on a problem. But before I get into the text, I kind of have to explain the topics of this section so that you kind of understand what we're talking about. And as I'm explaining the topics of this section, I'll kind of talk about something that I skipped over when we did section 12.5 because it wasn't really necessary there, and adding it there probably wasn't going to aid your understanding of the material. It might have just made it worse. So I have a bunch of things typed up for this lecture, and very specifically, I'll do a handful of problems outside the text, and then I'll get into the text and do some problems in the text. You'll really want to make sure you have your graphing calculator around because some of the computations in this section without a calculator are a bit tedious, so I'll rely on my calculator quite a bit. All right, so in section 12.9, I'm going to solve a few problems that aren't in the text to explain the difference between these problems and problems that we presented earlier. And the first problem I made up with 3 parts. The first 2 parts don't contain anything new, could have been done in section 12.5, so you might be able to do the first 2 parts of problem 1 without me doing any sort of lecture. And then the third part kind of talks about, it leads us into the new material for this section. So question 1 has 3 parts. The first 2 parts I kind of fit on this page, and these are the parts that theoretically you should be able to do if you pause the video and answer the questions. You should be able to get the same answers that I have. Your answers might be in a slightly different order because we're being asked to create a sample space, and the order that you write a sample space in is irrelevant. Just the number, the elements of the sample space are important. So for this problem 1, this is not from the book, this is just an extra made up problem. I have these 4 letters, I'm putting them in a hat, and I'm picking out 2 letters. The first one says, create a sample space if the letters are drawn without replacement, or with replacement, should I say. So I can pick a first letter. I'm going to do a tree to make this sample space, and then I can do a second letter. So my first letter can be either A, B, C, or D. And if I'm putting a letter back, my second letter can be still any one of the 4 letters. So if I get an A first, second I could still get an A, a B, a C, or a D. So some items in my sample space would be a double A, and then an A, B, A, C, and A, D. So double A, B, A, C, and A, D. If I did the same extension of my tree from the B, I could get a B first, then an A, B, then a B, a B, then a C, then a B, then a D. So the sample space here would have BA, BB, BC, and BD. And then with the C, I did a C first, I still can get an A, B, C, or D second. Because I'm replacing the C back in, I could still get a double letter. And lastly, if I did the D first, I still can get the A, B, C, or D differently, or afterwards. So this is the entire sample space. It has 16 items in it. And that's just kind of what it is. So that we could have done in section 12.5. Similarly, part B, I can also do without knowing anything new from this section. So B says the letters are drawn without replacement. So my first letter, I'm going to do my trees again. My first letter could be the letters A, B, C, or D. But I'm not going to get double letters here. So if the A was drawn first, my second letter can't be an A again because I'm not replacing. So the things that I could get with the A first are an AB, an AC, and an AD. And then similarly, if when I do my second letter, if the B was the first letter, I couldn't get a B for the second letter because I'm not replacing it. So I could just get an A, C, or D. So I could get a BA, a BC, or a BD. And then if I get the C first, I could get the A, B, or D second. So I can get CA, CB, and CD. And then lastly, I can get DA, DB, or DC. For what it's worth, I'll do the for what it's worth in a little bit. So anyways, these are the sample spaces. I could have constructed those sample spaces, 3 lectures ago, and that shouldn't have been anything that's new. What's different about section 12.9 is going to be contained in the next problem. So the next problem is part C of this, and it says the letters are drawn without replacement, and the orders the letters were drawn in doesn't matter. So in this case, for this particular problem, I won't write both A, B, and BA. Those are going to be considered the same. Picking the letters A and B, regardless if it's A first and B second, or B first and A second, will be considered the same. Similarly, picking C first and B second is going to be considered the same as picking B first and C second, so that just the letters that are drawn are important and not the order that I write them in. And then I make this parenthetical comment here. So lately, any sample space that we've listed previously, the orders that I wrote the items in they were important. But that's not always going to be the case. I try to write a small example here of when the order may not be important. And if I pick 3 students from this class to go on an all expenses paid trip to Hawaii, it wouldn't matter if you were selected first, second, or third. Just being selected is enough. So if I said Beth, John, and Joe were selected, that wouldn't be different than saying John, Joe, and Beth were selected. That wouldn't be different than saying Joe, John, and Beth are selected. All of these items are written, those 3 names are written in different orders. So that's kind of like writing a sample space in a different order, but it's still the same 3 people going, and the order that they were selected doesn't matter. So in order to create this sample space, what I'm going to do is I'm going to take the sample space from part B. Part B, the sample space that I created, had an AB, AC, AD, and then a BA, I'm just copying again, BC, BD, I'm just copying my answer for part B, and then CA, CB, CD, and DA, DB, and DC. So what I need to do is I need to omit anything that's a duplicate. And as I go through to write my answer for part C, I'll look at my sample space and see if there's the same letters written in a different order. Those are going to be considered the same. So the first item I see in the sample space is AB. I'm going to write that in my sample space for the answer to part B. But what I'm not going to write in my sample space for part B is BA, because that's considered the same. And there's no other one in my sample space that has the letters A and B. So now I'm done with the AB. And I'm going to move on to the next thing in my sample space from B, which is AC. I haven't listed the letters A and C together, so I'm going to list them in my answer to part C. And then I'll look through my sample space and see if I've listed those two letters in a different order, and I have. I'm not going to write CA in my answer to C because it's considered the same. Just having the two letters is enough. The order's not important. Now I'm done with that. I don't see any other ones. Now I'm going to go to AD and see if there's any other items in my sample space that have those exact two letters, and the DA does. I'm quickly running out of sample space. Now I'm going to go to the combination BC, cross out any combination of those letters written in a different order. That's the CB that's under it. And then I'll go to the next thing, DB. DB is the same letters as BD, so I'm not going to write those both. And lastly, the CD and the DC are considered the same. So the sample space for part C has these 6 components in it, and you could have written them all differently. It would have been equally correct if I said the sample space is BA, CA, DA, CB, BD, DC, because the order that I'm writing the letters in doesn't matter, just the letter pairs make a difference. So as the problems got more restrictive, their sample spaces get smaller. The first one had 16 elements in the sample space because there were 4 letters to choose for the first, 4 letters to choose for the second. The second one, where I was drawing letters without replacement but considering the order to be important, there were 4 letters to choose from the first, 3 letters to choose from the second, so there was 12. And the last example, which is really where we're headed for section 12.9, there are only 6. So as I add more restrictions, the sample spaces get smaller. So I'm going to do another problem, and I'm going to skip the without replacement part, because the without replacement part, the sample space would be bigger than I care to write. So we're not ready for the concept, not completely ready to jump into the new material. So I'll do one more example, and then I'll start getting into the new material. So problem 2 here, this is an example again that's not in the text. It's a similar example. I have the same letters A, B, C, and D that are in a hat, but now I'm going to draw 3 letters out, and I want to create my sample space. And I didn't do with replacement, because with replacement there'd have to be 64 elements in my sample space, and I didn't want to do that. So I'm doing the letters being drawn without replacement, and if it doesn't say whether the order is important or not, then I'm assuming the orders are important. So I'm going to draw 3 letters. So I'm going to have a first letter, a second, and a third. And I'm going to create my sample space. So my first letter can be A, B, C, or D. My second letter, once I use a letter, I'm not replacing it. So my second letter could only be, if A is first, it could only be B, C, or D. If B is first, it could only be A, C, or D, because I'm not allowed to repeat. If C is first, it could only be A, B, or D. And if D is first, my second letter can only be A, B, or C. Because I'm picking 3 letters, I need to make my branches go further. The next branch is picking an A first and then a B second, and then what I could pick is a C or a D, because I've already picked the A and the B. They're no longer able for me to select, but I could pick the B or the D. So let me start to write my sample space. Let me do red. So this part of the tree would be giving me an A first, a B second, and a C third, and also giving me an A first, a B second, and a D third. So now I'm done with this branch. I'm going to go down this branch. If I got an A first and a C second, I still could get a B or a D as the letters left. And this would give me an A first, a C second, and a B third, or an A first, a C second, and a D third. And now, from the getting an A first and a D second, I'd still have the possibilities of getting a B and a C third. So I can write an A first, a D second, and a B third, or an A first, a D second, and a C third. So now I'm done with the A. I'm going to do the B. So a B, then an A, and then I can do a CD. So this line of the sample space would be a B first, an A second, and then a C, or a B, A, and a D. Now I'll do this, B, C, A, D. So a B first, a C second, and then an A, or a B first, a C second, and then a D. And then BD is going to be AC. So a B, a D, and an A, or a B, a D, and a C. Now I'm done with the B branch. I go to the C. I get CA. I'll be left with BD. So you can get a C, an A, and a B, a C, an A, and a D. Now I'll do this branch, CB, AD. So it's going to be a C, a B, and an A, or a C, a B, and a D. And then this last part of the C, CD gets an AB. So it's going to be CDA or CDB. Now I'm done with the C branch. I'll do the DA. So if D is first, A is second, I still have the B and the C left. So I'd get a DAB and a DAC. The order that I write these in doesn't matter, so I'm just trying to make them fit in the spot room that I have. D and B allows me to still get A and C. So my sample space would have a D, B, A, and a D, B, C. And then lastly, DC. If I get a D and a C, I still can get an A and a B. So I'm going to get a DCA and a DCB. So there are 24 elements in that sample space if I counted all the ones that I listed. All right, so part B is asking me without replacement, just like part A is, but in part B, in addition to without replacement, the order's not important. So having the 3 letters written in any order is going to be sufficient, and switching the order is going to be not considered a new item. So I'm going to create the answer to B, I'm going to look at my answer to C and cross out duplications. So the first item I see in my sample space for part A, where the order was important and replacement wasn't allowed, is ABC. That item can go in my sample space for B, where order doesn't matter, but replacement is not allowed. And now I can't put any item in my sample space for B that has those 3 letters written in a different order. So I'm going to go through my sample space for part A to help me construct my sample space for B, because this has every combination, when order is important. I can get my answers for B by just taking the elements from A that I need. So ABC in part A is considered different than ACB, because it's the same 3 letters but in a different order. But here I'm not going to count it. So I'm going to not write down ACB in this list. Similarly, I'm not going to write BAC in this list because I already have the 3-letter combination. I'm not going to write BCA. I'm not going to write CAB, I'm not going to write CBA. All 6 of those are the same 3 letters just written in a different order, and I only need one of those 6 in my list. If you would have written ACB instead of ABC, that would be okay. Now I'm going to move on to something else that I haven't crossed out. I haven't crossed out the letters ADB, so that needs to be in my sample space because that's different than the line above it. And now I'm going to go through and strike out anything that has those 3 letters written in a different order because those won't be included in my answer to B. In B, just the letters are important, not the order. So the 3 letters A, D, and B occur in this one. It occurs in that one. It occurs in this BAD, this DAB, this DBA. I don't know if I have any more left. I don't think I have any A, B's, and D's left. So I think I've crossed out all the things from my sample space that have those 3 letters. I'm ready to move on to another combination. Here's another combination that I haven't used yet. I don't see those 3 letters A, C, and D grouped together in any of my sample space. So that's good to add to my sample space to part B. Now I'm going to cancel out anything that has those 3 letters just shuffled around. ADC has those 3 letters shuffled around. CAD has those 3 letters shuffled around. DAC, DCA, and CDA are all the letters A, C, and D just shuffled around in different orders. So I don't want to include those in this list. Another thing that I haven't included is BCD, so I'm going to include it. And then cross out anything that has those letters, like BDC, DBC, DCB, CBD, and CDB. That's it. The answer to part B is how many are there if letters are drawn without replacement and the order the letters were drawn in does not matter here. And hopefully I didn't say does that matter on the last one since I cut and pasted. It might have actually said that. The order, part C, the order does, again I was supposed to say not. Sorry about that typo. So in part C of number 1 and part B of order 2, it's supposed to say the order does not matter. Somehow that didn't get caught by Word because it's not a misspelled word. So when you add restrictions, when I did the with replacement to without replacement, the with replacement sample space is always going to be bigger than the without replacement sample space. So for parts A and B, the with replacement is bigger than the without replacement. I didn't do a with replacement for question 2 because the sample space would have had 64 elements and I didn't feel like writing 64 elements. So as I add restrictions, not replacing the letters reduces my sample space. Not replacing my letters and considering different orders as the same reduces the sample space even more. So I can list sample spaces for problems where the order is not important if I have the sample space for where the order is important, and then I could just delete the items that are considered duplicates. Our author won't, in the next 2 sections in 12.9 and 12.10, have us list sample spaces. What the author is going to have us do is compute how many items will be in the sample space without actually listing the sample space. So that's a skill that we need to have, and it's a skill that we have for some of the problems, but not all of the problems. So I'm revisiting the first problem. I changed the problem to number 3. Changing this word that to not. So I changed the question just slightly. In question 1, I posed this question, and I said list the sample space. Listing the sample space isn't something we're going to need to do in section 12.9. In section 12.9, almost every question that we're going to be exposed to is going to ask us how many items are in the sample space without listing. So one way to answer question 3A, how many items would be in the sample space for question 1A, I could just go through, look at my answer for question 1A. And 1A, I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There were 16 elements in the sample space that I listed for 1A. To find out how many, I could use the multiplication principle. I picked a first letter. I picked a second letter. And I picked a third letter. For the first letter, I can pick any of the four. Oops, I'm only picking 2 letters, so I don't need a third letter. For the first letter, I can pick any of the 4 letters, A, B, C, or D. If I'm replacing the letter, the second letter can still be any of the 4, A, B, C, or D. And if I multiply 4 times 4, I get 16 items that were in the sample space for 1A. For part B, that I still can do using the multiplication principle. When I go to pick a first letter and then a second letter, the first letter could be any of the 4 letters A, B, C, or D. The second letter, if I'm not replacing, could only be the 3 letters that are left. And there's going to be 4 times 3 are 12 items in that sample space. Part C, I can't get using the multiplication principle because of the order not being important. Doing the multiplication or the counting principle, when I multiply to get my number of items in the sample space, that inherently assumes that the order is important. And if the order is not important, the multiplication principle overcounts. And to figure out how to get the answer, that's what's new to section 12.9. So if the order doesn't matter and replacement's not allowed, this becomes something that we call a combination problem. Part B, where the order does matter and replacement doesn't happen, this is actually called a permutation problem. A permutation problem is taking a fixed number of items from a set and listing them where repetition's not allowed or replacement isn't happening and the order makes a difference. So this problem, one way to answer how many is to list out the entire sample space. If you list out the entire sample space, then you can get the answer. So for this problem right here, the answer to how many, I know because I did this problem by listing the sample space, so there should be 6 elements in this sample space. The question is, how do I get those? How do I get the answer 6 without listing? And this is where my calculator is going to come in handy. There's a formula that allows me to compute this answer built into my calculator, and my calculator understands that this is a combination problem. A combination problem is when I'm taking items, a fixed number of items from a set of items where I can't repeat an item and the order doesn't make a difference. So for this particular problem, our author will use this symbol C. And in this problem, there were 4 letters that I was picking from. And of those 4 letters, I'm picking 2. And repetition order wasn't important. And I couldn't use the same letter twice because I'm not replacing the letter. So if this is the case, if I can't use the same letter twice, it means repetition isn't allowed. And the order that I write the items in isn't important, then we say this is a combination of 2 items taken from 4. And to get this answer 6, I'll use my calculator. When I turn my calculator on and clear out anything that's in there, If I type the number 4, then hit my math key, and arrow either right or left to get to PRB. PRB means probability, and we're doing a probability chapter. And then if I go down to number 3, the NCR, that's kind of what I'm doing here. N is the number of items in the set that we're drawing from. R is the number of items that we're selecting. If I hit enter on NCR and then type the number 2, so from a group of 4 I'm picking 2, I'm not allowed to write the letter twice, and the order that I write the letter in doesn't matter, and I hit enter, it gives me this 6. I'll show you how to do this without a calculator, but it's a nuisance in a bit. Okay, so now I'm going to go to answer the questions of how many that relate to the first problem, the second problem we did. The second problem, we took the letters A, B, C, and D, picked out 3, and we did the letters without replacement, and then without replacement where the order of the letters does not matter. And if I want to refer back to my sample spaces, I can get the answer of how many by just looking at my sample space. So problem 2 and problem 4 are the same problem, other than problem 4 asks me to list how many, problem 2 wants the sample space. If I count the sample space that I created in problem 2, there's 2, 4, 6, 10, 14, 18, 20. There's 24 items. The answer to this question of how many ways are there to make 3 letters if order is important, even though it doesn't say that, and I'm not replacing the letters, the answer is 24. And the counting principle will work just fine for this particular problem. So for the first letter, I could pick any of the letters A, B, C, or D. For the second letter, I can only pick 3 because I'm not replacing a letter. So if I picked a letter, it's not available to me anymore. And for the third letter, I've already picked 2 letters. I'm not putting them back, so there's only 2 letters available for me. And 4 times 3 is 12 times 2 is 24. So the number of items in the sample space for this should be 24, and it actually has 24. Part B says how many items are in this sample space where the letters are drawn without replacement and the order the letters were drawn doesn't matter. The answer is 4. And in order to get that without having the sample space listed, I'm going to make this a combination problem. There were 4 letters. Of the 4 letters, I'm picking 3 of them. And I wasn't allowed to use a letter more than once because the letters weren't being replaced. And the order that I wrote the letters in doesn't matter. So that I'm going to call this 4 choose 3. And if I do that on my calculator, I hit the 4 button, type the math key, either use left or right arrows to get to PRB. And once you get to PRB, arrow down to number 3, hit enter. So this says from a group of 4 items, I'm picking where the order is not important and I'm not replacing, and I'm going to type the number 3. And when I hit enter, my calculator gives me the 4. So in a second, I'll show you how to do part B here with a formula, as well as part C for this one with a formula. So the counting principle that we use to multiply to get the size of the sample space implies the order's important. When we did section 12.5, I skipped over a symbol that looked like this that had the letter P. The answer for how many items are in a sample space if you're not replacing in an order is important can also be gotten on my calculator without doing the multiplication principle. So let me show you how to get this answer 12 and this answer 24 without using the multiplication principle or the counting principle. For using my calculator to not multiply 3 numbers to get the answer to 4A, or not multiply 2 numbers to get the answer to 3B seems silly to me, but it can be done. So if I wanted to get this answer 12, how many ways, without listing the sample space, this particular problem, when I'm taking letters from this group and I'm not replacing, but the order is important, that's a permutation problem. I could have done this. I said from the 4 items, I'm picking 2 items, or 2 letters. From the 4 letters, I'm picking 2 letters. I'm not replacing letters, but the order that I write the letters is important. This answer of there's 12 items in the sample space can be gotten by using this on my calculator. So this symbol right here between the letters, this says from the 4 letters A, B, C, and D, I'm picking 2 of them without replacement, and the order that I write the letters in is important. This says from the 4 letters A, B, C, and D, I'm picking 2 of them without replacement, but the orders I write the letters in is not important. If I did this on my calculator, I can get the number 12 without doing 4 times 3. To do that on my calculator, I type the number 4, hit the math button, arrow over to PRB, down to the NPR, type the number 2, and it gives me the 12 that I got for part B. I don't use this formula because my calculator isn't really saving me any time. It's a lot easier just for me to enter 4 times 3 than it is to do all those keystrokes. But any problem that we're doing without replacement in the order being important, you can do it via your calculator without using the multiplication principle or counting principle. Similarly, this part right here, A of number 4, I'm picking 3 letters from 4 letters. I'm not replacing the letters, and the order that I write the letters in is important. Our author would consider this as a permutation. From the 4 letters, I'm picking 3, and I'm not replacing, so I can't write the same letter twice, but the order that I write the letters in is important. If I did this on my calculator by typing the number 4, going to the math key, going over to PRB, down to NPR, hitting enter, typing the number 3, it's going to give me the 24 that we got in the sample space. So there are 2 features on my calculator that allow me to compute sizes of sample spaces based on how the sample spaces are being constructed. This one, the permutation, I just don't use that because it's easier for me just to multiply than it is to use the permutation feature on my calculator. But very specifically, what these letters are giving me, this is saying from 4 objects, I'm picking 3 without replacement, and the order is important that I write the objects in. The C says from 4 objects, I'm picking 3 without replacement, and the order that I write the objects in doesn't matter. So both of these can be gotten without a calculator using a formula, and I'll show you that formula, but you're not required to do that formula at all. Okay, so that's the warm-up for this section, and now we'll get into the section. The first few problems in the section ask me to compute some values that are kind of not part of word problems. Number 8 says find 7C2, and it really is written like this, 7C2, where the 7 and the 2 are subscripted, but I didn't subscript them when I was typing just because it was easier to type. So what this problem is asking me, it says, and how many items will be in the sample space if I select 2 items from a group of 7 items, provided order's not important and I'm not replacing. Once I take an item out, I'm not replacing it. And without replacement is similar to, or exactly has the same meaning as repetition is not allowed. When I pulled a letter out, A out, if I wasn't putting it back in, I couldn't use the A twice. Saying without replacement means you can't use something more than once. So I'll do this on my calculator, and then I'll show you how to do it by hand. You'll never have to do it by hand, but I'll show you how to do it. So I'm going to go 7, math, PRB, go down to number 3 and hit enter, then type in 2, And that tells me that in this sample space, there would be 21 elements. If I had the set that I was drawing from, I could create the sample space, and that sample space should have 21 elements. 10A, 8C2 says, this is asking me how many items would be in the sample space if I select 2 items from 8 items, and I'm not doing replacement, so I can't write an item more than once, and the order doesn't matter. I'll do this on my calculator, then I'll show you how to get them both without my calculator. So I'm going to go 8, math, PRB, go down to number 3, type in 2, and my calculator says it's 28. So the answer to 8 is the number of items in the sample space are 21. The answer to 10A, the number of items in the sample space is 28. The formula to do this is a nuisance, and it has a symbol that you may not remember. So the formula for this, to get this number 21 without my calculator, is this. It's going to be the left number factorial. That's an exclamation point there. I'll tell you about the exclamation point in a second. Times the difference of the two numbers, 7 minus 2 factorial, times the second number factorial. Factorial means to multiply starting at that number going down to 1. So if I was doing this particular problem and I didn't have a calculator, I take the left number, put it in the numerator with an exclamation point, subtract the two numbers, put them in the denominator with an exclamation point, and take the right number in the denominator with an exclamation point. The exclamation point means to multiply, starting at that number going down to 1. So in the numerator, 7 factorial means 7 times 6 times 5 times 4 times 3 times 2 times 1. In the denominator, this is 5 times 4 times 3 times 2 times 1 for the 5 factorial, and then 2 times 1 for the 2 factorial. If you're not using a calculator, then you start canceling. This 5 times 4 times 3 times 2 times 1 will cancel with that 5 times 4 times 3 times 2 times 1. And this 2 will cancel with that 6. 6 divided by 2 is 3. 2 divided by 2 is 1. I've canceled everything in my denominator except the 1, so my answer is not going to be a fraction. What I have left in the numerator, I didn't cancel the 7. The 6 turned into a 3. If I multiply that 7 and the 3, I get 21. Absolutely don't have to do these kinds of problems with the factorials because your calculator will do them. To get this answer of 28, I'd write the left numerator, or the first number in the numerator with the factorial or an exclamation point. Subtract the two numbers. 8 minus 2 is 6. Put that number first in the denominator with an exclamation point, and then the second number 2 I'll write in the denominator with an exclamation point. And now I'm going to expand. 8 factorial means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And 2 factorial means 2 times 1. I could cancel the 6, 5, 4, 3, 2, 1 with the 6, 5, 4, 3, 2, 1 if I'm doing this by hand. And this 2 and this 8 will cancel. The 8 will become divided by 2 and get a 4. The 2 will become a 1. What I have left is no denominator. I have a 4 and a 7 in the numerator. When I multiply that 4 and the 7, I'll get 28. So we can answer the question, how many items are in a sample space if repetition isn't allowed, that is, I'm not replacing when I'm creating my sample space, and order's not important, with my calculator, without my calculator, or by just listing the sample space. There aren't going to be any problems in section 12.9 where the author asks us to list the sample space. Every problem in section 12.9, the author is going to ask us the question, how many items would be in a sample space? And we're going to get that how many items without listing the sample space. The last part of number 10 I wanted to look at was this 8P2 that's in 10B. 10B asks me how many items will be in the sample space if I select 2 items from a group of 8 items, provided the order is important. That means if I change the order, it's considered different. And repetition is not allowed, or I'm not replacing. And in order to do this on my calculator, I type the number 8, hit the math key, go over to PRB, go down to number 2, that's NPR, type in 2 and hit enter, and I'll get 56. Formula for this, I take the factorial of the first term and write a fraction and put that in the numerator, subtract the two numbers and put that factorial in the denominator, and we'll never do P's or C's by hand because it's just a nuisance. And that's all that there is. It's just the left and the difference in the denominator. So 8 factorial is going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Cancel, cancel, fractions gone. I'm left with 8 times 7, which is 56. So the last half hour that I spent lecturing, in some sense, isn't going to help you on the test because there isn't going to be any problem that has you do those skills. I just felt obliged to try to explain what a combination is, and then to a lesser extent what a permutation is. So every question when I get into the text is going to be a how many question. A how many question is basically asking how big is the sample space. So write the size of the sample space without listing the sample space. And when I go through the problems, I'm going to try to justify the computations that I'm doing. So when I go to problem 22, it says an ice cream parlor has 20 different flavors. Cynthia orders a banana split. She has to select 3 different flavors. How many selections are possible? First of all, the order that I pick my ice cream in doesn't matter. If I pick vanilla, chocolate, and strawberry, or if I pick chocolate, strawberry, and vanilla, I'm going to get the same banana split just because, the fact that if my chocolate is in the middle, or my strawberry is in the middle, or my vanilla is in the middle, it's still considered the same banana split. So having a chocolate, strawberry, and vanilla ice cream banana split is the same regardless of where the scoops of ice cream are placed. And by the author saying different flavors, she's saying without replacement here. She's saying that once I pick an ice cream, I can't use it again. So he's saying, he's implying that all my 3 scoops have to be different. This makes this a combination problem. And to answer how many, from the 20 different ice creams, I'm taking a group of 3, and the order that I tell the person that I want the ice cream in doesn't matter, and I'm not allowed to use a flavor more than once, so I'm not going to be so they go without replacement. Without replacement, sometimes we just say repetition is not allowed. It has the same meaning. But this is a combination problem very specifically because it meets these 2 things. I'm trying to figure out how many items are in the sample space. The order that I select my ice cream in doesn't matter. I'm not allowed to do the same flavor more than once. If I was allowed to use the same flavor more than once, then this wouldn't be a combination problem. So now I'm going to figure out the size of the sample space, and I'm not going to use the formula. I'm going to use my calculator. But type the number 20, hit the math key, go over. I go left to get to PRB, down to NCR, hit enter, type the number 3, and if I actually had all 20 flavors and I wanted to list all the different banana split combinations of ice creams that the author could, that Cynthia could have, that'd be 1,140. So it'd be impractical to list the sample space, but I can tell you how many items are in the sample space without actually listing it. 24. Although it's a completely different context, it doesn't talk about banana splits. It talks about essay questions on a test. And apparently a test has 5 essay questions. A student has to pick 4 of them. And in how many ways can she do this? And I have to ask myself, does it matter the order that I pick my questions in? So if I answer question 2 first, then question 1, then question 5, it doesn't matter the order that I answer my questions in. Once I get my questions answered, the teacher, when they grade it, shouldn't be able to tell which question I answered first, second, third, and fourth. So the order isn't important that I answer the question in, because they won't be able to tell. When I'm grading a test, I can't tell which question you answered first, second, third, or fourth. It doesn't matter which order you answer them in, just as long as you get them answered. And I can't, once I pick a question, I can't answer it twice. So we say without replacement, or I can't repeat a question. So if I was missing my sample space, like I answered question 3 for my first question, I couldn't answer it again. So this is another without replacement, because once I pick a question, I can't pick it again. That makes this a combination problem. So this is really, I'd say it's a without replacement, or repetition is not allowed, is the same thing. So this is a combination problem, because the order that I select my questions in doesn't matter, and once I pick a question, I can't pick it again. Just like in the letter problem, once I pick a letter, I couldn't pick the letter again, and the order didn't matter. So of the 5 questions, I'm picking 4 of them. And how many ways are there to do this? Type my feet, 5, math key, arrow over to PRB, down to number 3, hit enter, type in 4, and there's only 5 ways to do this. So I'm going to keep just going through the problems, and every time I get to a problem, I'm going to try to justify that it's a combination problem. Every problem in this homework is a combination problem, so that I really don't even need to justify it, and I can get the answer, but I'm going to try to justify it, because on a test, the problems are going to be scrambled, and you'll have to be able to differentiate between when you can multiply to figure out the size of the sample space and when it's a combination. So 26, visiting New York City, the NY Gents want to attend 3 out of 10 plays. I'm assuming they're not going to see a play twice, and the order that they select the plays that they're going into doesn't matter, just the plays that they're going to see. So the fact that I see, the Book of Mormon first, and then Wicked second, and then Cats, even I guess those are at least plays, third, that's not different than saying we're going to go see Cats, the Book of Mormon, and then Wicked, if that's what I picked. So anyways, the order is not going to be important. Just the 3 plays that they pick are going to be the important part. And I'm assuming they're not going to see the same play twice to count those of those 3 plays. So that makes this a combination problem. And of the 10 plays, they're going to pick 3 of them. And how many different sets of plays can they pick? Just go right down and do 10C3, and I get there's 120 different combinations of plays. So if you want to work ahead, you might be able to get a little ahead, but there's going to be a roadblock that's going to slow you down. And that roadblock comes real quick here. It comes on problem 36. So you might be able to do, I'm going to do problems 28 and 30. Those problems fit perfectly to the problems that I've done so far, but 36 is a little bit different, and you might not be able to do that without me showing you how to do it. So 28 talks about Mary. She purchased maybe like 24 petunias, and she's going to only plant 20 of them, because they sell you like a brick of plants when you get them. It's usually you buy, you get a bunch of plants, and for some reason she only has room for the 20. And how many ways can she do this? This is also a combination problem. Just the 20 plants that she picks matters. Maybe there's 4 plants that don't look as healthy as the others, so she's not going to pick those. She's going to pick the 20 healthiest looking plants. But the order that she picks them in doesn't matter. Just the fact that she picks them is enough. And I can't pick the same plant more than once, so it's not replacing. It's not like I'm going to pick it, put it back, and pick it again. So this is a combination problem. Of the 24 plants, I'm picking 20 of them. It's combination because the order that I select the plants in doesn't matter, just the plants that are selected matters. And I can't select the same plant more than once, just like not picking the same letter more than once. So I do 24, math, C, 20, and 10,626 different groups of 20 plants that she can select. So this book is starting to get dated because CDs are starting to become a thing of the past, since we mostly just do our music, online now and throw them on our iPod. But back when this book was written, iPods were just getting started, and so we actually bought CDs. So Neil wants to purchase 6 CDs, compact discs that have music on it, not like savings bonds or investments at the bank. And he only has enough money to purchase 4. And how many ways can he do this? Well, I'm assuming that when I pick my 4 CDs out, it doesn't matter that I, picked, God, I won't even get into albums. Neil Young Harvest, Pink Floyd Animals, that's got to be enough. Those are 2 of my favorites. Not that it matters. But anyways, it doesn't matter the order that you select the CDs in. When you bring them up to the register, they won't even be able to tell the order that you selected the 4 CDs in. They'll just be happy that you're buying them. And I'm assuming I'm not going to buy 2 copies of Pink Floyd Animals, so I will assume this is a combination problem, because I'm not, once I select, I can't select a CD more than once. So from the 6 CDs I'm thinking about, I'm picking 4 of them. It's a combination problem because I'm not going to pick the same CD more than once, and the order that I select them in isn't important. And there's 15 different groups of CDs that he might get. So 36 is where it gets difficult in some sense, because there's numbers in the problem that don't get used. So in every combination problem that we've done so far, I didn't really differentiate between the items I was selecting. I was picking 20 of 24 plants, 4 of 6 CDs. 36 and on, I'm differentiating what I'm picking from a little bit. So in 36, 12 people are going to be given a drug, 6 men and 6 women. And so I'm picking 12 people, but specifically 6 men and 6 women, and there are 10 men and 9 women that have volunteered to be given the drug. And how many ways can a researcher do this? If I did 12 choose 6, because the order that you're selected in doesn't matter, and you can't be selected twice. I mean, once you're selected, you can't be counted twice. If I did this 12C6, that would be how many ways, if I did this, 19C12, there's 19 people, 10 men and 9 women, and I'm given the drug to 12 of them. If you did 19C12, that doesn't restrict me. This tells me I'm giving 12 of the 19 people the drug, that the order that I select them in doesn't matter, just the fact that they're selected matter, and the same person can't be counted twice. Once I pick a person, I can't pick them again. If you did this wouldn't differentiate between men and women, and the 2 numbers, 19 and 12, aren't going to be in my answer anywhere. You don't see the 19, so that's not a tempting number to use, but you do see the drug being given to 12 people. I'm giving the drug to 12 of the 19 people, but very specifically 6 men and 6 women. And when you're splitting up the distribution into distinct components, here the CDs weren't differentiated, but in this particular problem, I very specifically need to give 12 people the drug, but it has to be 6 men and 6 women, and I've got 19 people to choose from. To get this answer for the women, I need to give 6 women the drug and I need to give 6 men the drug, the number to the right of the C is how many are given the drug. There's 12 people that are total that are going to be given the drug, 6 women and 6 men. There's 19 people to choose from, but for the women, I'm picking 6 of the 9 women. For the men, I'm picking 6 of the 10 men. So when I have a specific look of what I want to accomplish, I need to separate the look. So I'm giving the drug to both women and men, 6 of the 9 women, 6 of the 10 men. The 6s at the right end add up to the 12 people that are getting the drug. The 19s, the 10 and the 9 add up to 19 of the 19 total people. I'm going to do each of these combinations separately. So I'm going to do 9 math, probability, enter 6. That gives me 84. And then I'm going to do the men separately. And I'm going to multiply the numbers together. So to answer the 36, you get by doing 2 combinations, because there's 2 different kinds of people that are getting the drug, and you multiply the combinations together. The rest of the problems in this section are going to be this style of problems. They're all going to be combination problems, because the order that I'm selecting is not going to matter, and I'm not allowed to select the same item twice. But I'm going to be having to make multiple combinations because I'm specifically told how I need to select. "38 talks about Mike. He goes to the store. He needs to get 3 different bottles of regular soda and 3 different bottles of diet soda. And there's 10 different types of regular soda, 7 different types of diet sodas. So when Mike goes to the store and gets the 3 regulars and the 3 diets, I'm assuming the order that he selects the item in doesn't matter. And he's not going to get 3 bottles of Diet Coke and 3 bottles of Sprite, because the word different implies once I pick a bottle of a certain pop that I'm not going to get it again. So the different implies that I can't get the same item more than once, or it's like without replacement. Once I pick Coke, I can't pick it again. And the fact that I assume that the order I pick the sodas in doesn't matter, just the fact that I have these 6 different sodas, the 3 diet and the 3 regulars, is fine. So it's a combination problem, but I'm getting different looks. Just like I separated men and women, in this problem, I need to separate the diet soda from the regular soda. If I don't separate them, then I won't get quite the right answer. To the right of each is the number of each kind that I'm picking. I'm picking 3 bottles of diet and 3 bottles of regular for a total of 6 bottles. And to the left, there are 7 bottles, different kinds of diet, and 10 different kinds of regular that I have to choose from. I'm going to compute each one of those combinations separately and then multiply them together. The first combination comes out, well, if you actually know how to type it in, the first combination comes out to 35. The second combination comes out to 120. And if I multiply 35 times 120, I'll get the different. So when Mike comes home with his 6 bottles of soda, there are actually 4,200 different groups of 6 sodas, having 3 diets and 3 regulars that he could have came home with. Committees are super common combination problems. So I'm forming a committee. If I get selected to be on a committee, it just generally matters that I'm selected. So if I pick 5 of you to put on a committee to, design a party, just being on the committee is enough. The order that you get put on the committee doesn't matter. And for this committee, it has to have 2 teachers and 3 students. This is a combination problem because getting put on a committee, being on the committee is enough. The order that you get selected to the committee doesn't matter. And you can't count as 2 people on the committee. Once you're selected, I can't put you back and select you again. So it's like a without replacement. The order that doesn't matter. So how many committees are there? I need 2 teachers of the 6 teachers to choose from, and I need 3 students of the 50 students to choose from. So I'm going to do 6 choose 2 times the 50 choose 3. 6 choose 2 comes out to 15. 50 choose 3 is going to be a bigger number. Comes out to 19,600. And when I multiply those results, I'll get how many different committees. You know, each committee is different if it has at least one person different than another committee. So there's 294,000 different committees possible. When I wrote the take-home test, I snuck a few card problems on there because in card problems, it's so tempting to want to put 52. The very first time I ever had to teach combinations was in college algebra at NAU when I was a grad student, and I didn't know how to do the problem, so I had to ask a teacher to explain to me. And card problems, I think, are the hardest combination problems, but the most common combination problems. If you ever decide to go on for your master's and you have to take a test to get admitted to a master's program, specifically the GRE or the GMAT, guaranteed that there's going to be a math section on those tests, and guaranteed that they're loaded up with probability and counting problems. So this particular chapter, if you're ever going to grad school, you'll want to have your notes handy when you go to study for those particular tests, because those tests are weighted heavily for combinations and permutation kind of problems. Also, they're weighted heavily in geometry. So being familiar with these is good. So very specifically, this problem, these 3 problems are card problems. They may not look like they're combination problems, and they may not look like they need more than one combination, but for each one of these is a combination problem. So first of all, a five card poker hands means if I give you 5 cards, how many ways are there to give you 3 spades and 2 diamonds? And I so want to put 52 somewheres in my work, because I know that there's 52 cards in a deck of cards, but 52 for each of the 3 problems I have on this sheet won't appear anywhere. The 5 is going to appear in hiding. So what I want to do is I want to create a poker hand, and if I have 5 cards that are dealt to me, the order that I get a card isn't important. The 5 cards are important, so the order doesn't matter because I can shuffle the cards around in any order I care. And it's a without replacement problem, because once I get a card, I can't get 2 of the same card, so I can't put it back and get it again. And the 5 is going to come up from getting 2 diamonds, or getting 2 diamonds and 3 spades. So the 5 cards that I'm getting is buried in the 2 diamonds that I get to the right of the C for the diamonds, and the 3 spades is buried to the right of the C in the spades. 52 doesn't go anywhere in this problem because I'm only considering diamonds and spades. To the left of the C's, I get the number of that card that appears in the deck. A deck of cards has 13 diamonds and 13 spades. The number of hands that have 3 diamonds and 2 diamonds and 3 spades can be gotten by multiplying those 2 combinations. The first combination gives me a 78. The second combination gives me a 286. And if I multiply 78 times 286, I get 22,308 different 5-card poker hands. Doesn't really even need to say poker, that have 2 diamonds and 3 spades. The next 2 parts I'm going to do exactly the same way. I'm making 5-card poker hands. And for each of my poker hands, I have a very specific 2 sets of cards that I want. For the second one, my 5-card poker hands need to have aces and kings. To the right of the C's, I want the number of those cards that I need. I need 4 aces and 1 king. To the left of, so that's the 5 that comes in this problem. 52 won't be anywhere in this problem. To the left of the C's, I put the number of those cards that are available in a deck. And there's 4 aces and 4 kings in a deck. And if I do these on my calculator, I'll get 1 and 4 for the combinations, and I'll get 4. So if I did 4 math C4, that gives me 1. And if I do 4 math C1, I get 4. Did I do those backwards? 4C4 is 1. I did them right. And then, okay. And then for the last one that I'm doing that hopefully is going to inspire you when you get to the test, I want to have 3 face cards and 2 aces. I know that there's 4 aces. Our author doesn't consider an ace a face card because it doesn't have a picture with eyes on it. Face cards are jacks, queens, and kings. There's 4 of each, so there's 12 face cards. To answer the last question, I need to get 3 of the 12 face cards and 2 of the 4 aces. The 5 cards are buried in the right-hand side. 52 doesn't come in anywhere because I'm only considering face cards and aces. I'm not considering the rest of the deck. So if I did this, 12 math C3, I get 220. And then 4 math C2, I get times 6. If I multiply those together, I get 1,320. When we do the next section, it's going to feel quite a bit like this section. I'm pretty sure every problem in the next section, section 1210, is also a combination problem. But the words in this section, every question I did, other than the beginning problems where I asked you to list the sample space, every question somewhere said how many, and how many kind of is not a fraction problem. It's just a problem where I'm computing a number. In section 1210, the question how many is going to be replaced by the question what is the probability? And when the question of how many is changed to what is the probability, then your answer is going to have fractions in them. So it's going to feel very similar, the next section, to this section, in that there's going to be a lot of combination problems, but all of my answers in section 1210 are going to be fractions because the questions say how many, whereas none of my answers in section 12.9 were fractions because how many doesn't imply fractions, but the word probability does have fractions. So when you watch the video from 1210, and when you do the take-home test, you have to very specifically look at the question and see if it's a question that comes from 12.9 or 12.10, if it's asking how many or what is the probability. How many is not going to be a dividing and a fraction problem, but what is the probability is. All right, so hopefully that will help you through the homework and then the take-home test when we get that